All right, welcome to Rationals Day 2. We're in the same sweatshirt because I walked over there and click stop and then click record again. So Rationals Day 2, we're going to continue talking about vertical and horizontal asymptotes, but today we're going to add in holes and intercepts, both x and y intercepts. Okay. So we're kind of going to jump around. I think in total for this one, I'm going to go through 4 examples, with the 4th one I go through being the hardest one to work through. So if you get a rational function, before you start worrying about all this stuff, first try to get this a little bit simplified form. So see if you can start factoring both the top and the bottom. So I would recommend that if you haven't gotten good at the guess and check method yet for factoring, that you practice that. So when we factor this top, the x terms have to multiply to be 2x squared, which means one of them is going to be 2x, one of them is going to be x. From there then, these two other numbers that are by themselves, these have to multiply to -3. So it's got to be 1 and -3. You just got to figure out whether the positive one's going here, the -3 is going here, or positive 3 is going here and the negative 1's going here. Okay? So this one would factor into the first way I mentioned. So 2x plus 1 and x minus 3. So factor the top, factor the bottom, difference of squares, or adds to 0 multiplies to -1. So x plus 1, x minus 1. So we factor both the top and the bottom. Now, the first thing we want to look at, to continue simplifying this, is anything the same on top as it is on the bottom? Well, in this case, there's nothing that's the same on top and bottom. There's no linear factor that's going to cancel out. Okay? So start with the domain. So domain-wise, here, x can't be -1. Here, x can't be +1, because otherwise it would make the denominator 0. So domain-wise, 2 different ways you can write it. I'm going to show you what my preference would be just because we get to more advanced ones. So if x, so I'm going to off the side here. So x can't be -1, x can't be +1. So in earlier chapters, we wrote the domain as from -∞ to -1, between -1 and 1, and then from 1 to +∞. Okay, that's fine if you want to continue writing it in that notation. It's more descriptive, but another notation would be to say all real numbers except -1 and 1. So all real numbers minus except -1 and 1. So this is telling me every real number works except these two numbers, x values. Okay. So next, vertical asymptote, kind of hand in hand with the domain, is if it can't be -1 and 1, that means because nothing went away here, that there's going to be vertical asymptotes at -1 and +1. So vertical asymptote at x equals -1 and x equals +1. A hole would appear if there was a linear factor on top that was the same as a linear factor on the bottom. So if we were able to take something off. In this case, we weren't able to do that, so there are no holes. Okay, none. Horizontal asymptote. So from yesterday, this is where we look at the relationship between the degree of the top and the degree of the bottom. So because these are the same degree, the horizontal asymptote will be the coefficients. So 2 over 1, so y equals 2 over 1, or just y equals 2. Last thing, intercepts. So we got to check for both y-intercept and x-intercepts. So for y-intercept, well, y-intercept is going to happen when x value is 0, right? So all we're doing is finding f of 0, so we're putting 0 in for all the x's in the rational function. Okay. Now once you see what's going on here, if you want to not show all this work, that is fine. So we're plugging 0 in, right? This is going to be 0, this is going to be 0, it's just going to be -3. Bottom, 0 squared, 0, it's just going to be -1. So f of 0 equals 3. So that means one of the intercepts, in particular the y-intercept, is going to be at 0, 3. Okay? Now, the x-intercept, I'm going to erase this so I can just write up a little higher. For the x-intercepts, it's going to be when this function equals 0. Okay, we're setting the entire rational function equal to 0. Now, technically 0 is over 1. So shorthand-wise, we can always, to get the x-intercepts, we can always just set the numerator equal to 0. Okay? Because the denominator can't equal 0. That's when it's undefined. We dealt with that over here. But when the numerator equals 0, that's when it's going to tell you where it's crossing the x-axis at. Now, would I want to set this original numerator equal to 0 or the factored numerator equal to 0? Hopefully you're thinking factored, because if you set this equal to 0, you're just going to factor it and then solve it. So I'm setting the factored numerator. This is to get the x-intercepts. I'm setting the factored numerator equal to 0. Well, if both these things multiplied together equal 0, either the result of this was 0 or the result of this was 0. So from there, either 2x plus 1 equals 0 or x minus 3 equals 0. Solving this, subtract the 1, divide by the 2, we get x equals -1/2, and here x equals 3. So if these are x-intercepts, both of these are going to have y value 0. So the x-intercepts, one of them is going to be at -1/2, 0, and the other one is going to be at 3, 0. Okay. So we're done with that one. We got domain, vertical asymptote, hole, horizontal asymptote, and intercepts. Okay, second one, I'm going to go in order for this one, and then we're going to jump for the next example. Okay, so for this one, again, start with factoring, if we can factor it. So if you want to pause the video and factor it, great. If not, I'll just go through it. So factor the top, adds to -1, multiplies to -20. So this would factor into x minus 5, x plus 4. Factor the bottom, adds to -3, multiplies to -10. So we get x minus 5, didn't need the other set of parentheses there, x minus 5, x plus 2. So now in this one, we have an x minus 5 on top and x minus 5 on the bottom. So those are going to go away. And I would urge you to write, if something goes away, write what you're left with as a different function. So in this case, let's say g of x is x plus 4 over x plus 2. Because there's some things that are going to be based on the original function, there's going to be some things that are based on this new function after we take that out. Okay? So first thing, domain. Domain is based on the original function. It's on this original function. So for the domain, it's going to be all real numbers, except here x couldn't be 5, here x couldn't be -2. So domain, all real numbers except 5 and -2. Now, vertical asymptote. Vertical asymptote is based on the new function. Okay? Because this will deal with here. So vertical asymptote now, we're just based on this new function, so there's just a vertical asymptote at the -2, this x value that it couldn't be. Because the whole is coming from the linear factor that was the same on top as it was on the bottom. So there is a whole at an x value of 5. Now, just because we know there's a whole at the x value of 5, we got to figure out what y value is that at. So for the whole, we can use this new function, because that's the function that's going to get graphed. So we're replacing the x's in this function with the x value of 5 that the whole was at. So g of 5 would equal 5 plus 4 over 5 plus 2. which means the y value is at 9/7. So the whole is at x value 5, y value 9/7. Okay? Horizontal asymptote-wise, degree top was the same as the degree bottom, which means we're dividing the coefficients that are in front of there. So horizontal asymptote, y would equal 1 over 1, which equals 1. So horizontal asymptote at 1. Okay, intercepts. We'll start with y-intercept. So we'd be concerned with when is this function, when is the x value 0? So if we put 0 in, we're going to get 0 plus 4 over 0 plus 2, 4 over 2 equals 2, which means the y-intercept of this function is going to be at 0, 2. Okay, x-intercept wise, again, we're concerned with when is the top of the function, x-intercept, when is the top of the function going to equal 0? So that's going to happen, subtract the 4 over, that's going to happen if x was negative 4. So then x-intercept wise, x value negative 4, y value 0. Okay? Maybe it needs to be said, but for any x-intercept, y value 0. Okay. Okay, let's jump to number 5. Jump to number 5. 5's a little bit more complicated. Okay, again, even if you think you've got it right now, I would stick through the end of this video because the next two are drastically different than the first two. All right, this one. First, let's see if we can factor it. So the top one to factor, that might take you a little bit of time if you're not as familiar with the guess and check method. Because this could be 10x and x, it could be 5x and 2x, you'd have to try some things. Ends up factoring into 5x plus 3 and 2x plus 1. So you get 10x squared plus 5x plus 6x, that's the 11x, and then the plus 3. Okay, bottom, we got a cubic. So hopefully we can see that, okay, we got a cubic, but all three of these have an x, so we can factor out an x. So we get x times 3x squared plus x minus 1. And then unfortunately, this quadratic you're left with after you factor the x out can't be factored any further. So we're kind of stuck there. So domain-wise, x down here, this can't be 0, because then you'd have 0 times that, make it all 0. So right away here, x can't be 0. But we also need to figure out, like, okay, this can't be factored, but what values of x here are going to make that parenthesis equal to 0? So we need to know when is this quadratic, 3x squared plus x minus 1, when is that going to equal 0? Because it can't equal 0. So since it's unfactorable, trust the old quadratic formula. So x cannot equal opposite of b plus or minus square root b squared minus 4 times a times c all over 2a. Okay, so plug the stuff in underneath the square root. We get 13. This is even messier because it doesn't come out to a nice number. That's why it was unfactorable. Okay, so we know x can't be 0. And then from quadratic formula, x can't be negative 1 plus or minus the square root of 13 over 6. So domain-wise, all real numbers except 0 and negative 1 plus or minus the square root of 13 over 6. Okay, now vertical asymptote-wise. Okay, is there gonna be any holes? Hopefully you're thinking no, because there was no linear factors that went away. So there's not going to be any holes. Which means all three of these, the one here and the two that are here, are going to be vertical asymptotes. So vertical asymptote at x equals 0, at x equals negative 1 plus the square root of 13 over 6, end at x equals -1 minus the square root of 13 over 6. So this one has 3 vertical asymptotes. All right, horizontal asymptote. Horizontal asymptote, we look at the highest exponents. So this one is bottom heavy. The degree of the x down here is larger than the top, bottom heavy, which means horizontal asymptote y equals 0. Okay, intercepts. So intercepts, we want to find, if we started to find the y-intercept first. So if we try to find f of 0, well, what's going to happen now if we put 0 in for all of these x's? Well, I'll put it in just so I can show you what's going on. So on the top, we're fine. We're going to get +3. But on the bottom, we're going to get 0 plus 0 minus 0. So we're going to get 0. So the y-intercept is undefined, which makes sense because there was a vertical asymptote at 0. So this one is not going to have, there is no y-intercept. Now x-intercept wise, so that was y-intercept. X-intercept wise, we're setting the top of this function equal to 0. And again, it makes more sense to set the top here because it's already factored. So for this one, 5x plus 3 times 2x plus 1 is going to equal 0. So setting each of these equal to 0, we would get -3/5 and -1/2. So we do get 2 x-intercepts, -3/5 0 and -1/2 0. But no y-intercepts because there was a vertical asymptote at 0. Okay. I'm going to do one more example. I got about 10 minutes left in the school day, so hopefully we can squeeze it in. Okay, number 8 for this monstrosity. Okay. All right, so we got quadratic on the top. So we can factor that. So top's going to factor, adds to 4, multiplies to 3, so we get x plus 1, x plus 3. Now the bottom here is the issue because we have a cubic. So you could start with trying to see if this cubic will factor by using factoring by grouping. So let's see if the bottom one, if this factors. So grouping, we would group the first two, group the second two. Within this first parenthesis, take out what they have in common. So they have an x squared in common. There'd be an x left. There'd be a 2x left here. Take an x squared out of here. There'd be a 5 left. Here, this would have to be, what's left in here would have to be 2x plus 5. Okay? So does this factor? Doesn't look like it, because to go from here to here, I'd have to divide by -3. And to get from -3 divided by, or -9 divided by -3, that'd be +3. Doesn't work there. Okay, so it doesn't factor. But that's the first thing to check, because that way, if that works, that's a lot faster than what we have to do with this one. Okay, so because it doesn't factor, we now need to try to figure out, we need to get this cubic, we need to take a linear factor out, and we need to get it down to a quadratic. So this is the stuff from the previous chapter where we have to use the rational root theorem and then use division to take one of those linear factors out to get it down to something that's squared. So possible roots, factors of 2, 1, and 2, factors of 9, 1, 3, and 9. So possible roots, we'd have plus or minus 1 divided by 1, plus or minus 1 divided by 2, plus or minus 3 divided by 1, plus or minus 3 divided by 2. So we've done that process a lot last chapter. So you'd have to test those roots and find one that works and then do division. So turns out that -1, which might have been the second one you tried, if you tried 1 first, hopefully you tried -1 next. -1 is the factor that works, or the root that works. So if we divide by that root, I'm going to use synthetic division just because I think it's a heck of a lot faster. So -1 worked. When I put -1 in for these x's to test it, I got 0. So bring the 2 down for synthetic division. 3, multiply, add, multiply. Okay, so -1 was a root, which means the bottom of this, one of the roots was -1. So as a linear factor, that's x plus 1. And then the rest of that quadratic would be 2x squared plus 3x minus 9. Okay, and you got some room here, so I'm just going to erase just so I can keep writing pretty high here. All right, so we had to use synthetic division to get one of these linear factors to come out, so now we're down to a quadratic. Now check to see if that quadratic can be factored, which it can. So we'd have x plus 1 on the top with x plus 3. On the bottom, x plus 1, we'd have what, 2x plus 3? 2x minus 3. And x plus 3. So there we'd get the 2x squared, the plus 6x minus 3x, so that's that, and then the minus 9, that's that. Okay. So now, once we finally got to here, factored the top, division to take out a root down here, to get it to a quadratic, to factor that quadratic, to finally get it all broken apart. Now we can actually focus on the rational stuff here with the domain and the other stuff. So domain. So here x can't be -1. Here x can't be 3/2, and here x can't be -3. So domain is all real numbers except -1, 3/2, and -3. Now, remember not to go right from domain to writing the vertical asymptotes, because one of these could be a hole. So linear factor x plus 1 was the same on top as it was on the bottom, which means that's where the hole is at. So take that away, x plus 3 on top, 2x minus 3, x plus 3 on the top, or on the bottom, sorry. So hopefully somebody's catching what's going on here. So here, x plus 1 went away. Could be more than one hole though, right? So here we had also an x plus 3 that would go away, which means this is going to simplify all the way down to 1 over 2x minus 3. So now both of these that went away, that's where the holes are at. So there's going to be hole at -1, we'll figure out the y value. There's going to be hole at -3, we'll figure out the y value. So the only vertical asymptote was this one linear factor in the bottom that didn't go away. So x equals 3/2. So these other two values that were the restrictions on the domain, those were holes. The one that wasn't a hole is the vertical asymptote. So hole-wise now, we got to figure out what are the y values at those x values of the holes. So g of -1, so we're going to plug -1 into this function. 1 over 2 times -1 minus 3. So we get 1 over -2 minus 3, -5. So we get a hole at -1, -1/5. And then we'd also have the hole at -3. So 1 over 2 times -3 minus 3. So -6 minus 3, -9. So a hole at -3, -1, 9. So we got two holes. All right, horizontal asymptote. Come back to the original rational function, x squared on top, x to the third on the bottom, so it's bottom heavy, which means there's going to be a horizontal asymptote at y equals 0. Now, intercept-wise, so y-intercept, we would start with plugging in, so y-intercept, we want to know when does the function have an x value of 0? So 1 over 2 times 0 minus 3. So that's gone, so negative a third. So at 0, negative 1/3, there would be a y-intercept. Okay, x-intercept wise, we're concerned with when is the top of the function going to equal 0? Well, after all this stuff goes away and we get down to here, the top of the function, 1, is never going to equal 0, right? That's not possible, which means there are no x-intercepts on this graph. There's only a y-intercept. Okay? All right, I realized that was probably overload. That was a lot, especially once you get into, you start incorporating the holes and the intercepts, it gets to be a lot. Okay, but again, so that leaves you with number 7, 5, 6, and 7 to work on. Leaves you with number 3 and 4 to work on, so 4 problems. Okay, again, if you have questions, that those in your group or those in the class, if you can't get them answered, please reach out and ask. I'll be happy to provide answers when I'm done for the day, and I can address those questions. Okay. Tomorrow is going to be a class review activity, so use each other, work together through that. So there will not be a video tomorrow. Next video will be day 4 when we start to talk about oblique and horizontal asymptotes. Okay? I hope everybody has a great Tuesday.